Hello students, welcome to my session. My name is Eswanaja, lecturer in physics from Government Polytechnic Nirmal. Today I am going to explain the simple harmonic motion. Simple harmonic motion. So to explain this simple harmonic motion, first of all, what is the content of this session is the periodic motion. First of all, we are going to know the what is meant by the periodic motion. Then we going to learn about the simple harmonic motion. Then the projection of uniform circular motion is a simple harmonic motion. And finally, what is the displacement of the particle in the executing simple harmonic motion. So these are the topics we'll discuss in this session. First of all, the periodic motion. Periodic motion is the motion which repeats at regular intervals of time. We'll see so many types of periodic motions, means the motions in our daily life. Suppose the motion of the fan in a room, and the motion of the clock, hands of the clock in the clock. Next, the vibrations of the tuning fork, and we know that Earth revolving around itself, and it is around the sun also. And these, if you observe these motions in our daily life, so these motions are repeating continuously at regular intervals of time. Means, suppose if we observe the motion of the Earth around itself, the rotation around itself, it is repeating after 24 hours. The Earth spinning around its axis, its own axis, and it is repeating after 24 hours continuously. After 24 hours, it is repeating the same motion. And if you observe the rotation, the revolution of Earth around the sun, the motion of this Earth around the sun, it is repeating after 365 days, means after 1 year. Means if you observe the hands of the clock, so the motion of the clock hands will be repeating after 12 hours. So if you observe these motions, what you observe here, the motion, it is repeating at regular intervals of time. So this type of motions are called as periodic motions. So you can see the examples in this slide here. You can observe the clock here, wall clock, and here Earth is the motion of the Earth around itself, and the motion of the moon around the Earth, and Earth revolution around the sun also. So here in this figure there are 4 type of periodic motions. The moon is moving around the Earth, and Earth is spinning around itself, and Earth is moving around the sun. So 3 types of motions, the periodic motions are there in this figure. And there is one more example, that is wall clock. So this is the periodic motion, means the motion which repeats at regular intervals of time is called periodic motion. And the examples of periodic motion. So the examples of the periodic motion of the rotation of Earth around its axis. See, the rotation of moon around the Earth. Then the revolution of Earth around the sun. Already I explained these 3 examples. Then we go for the next one, the beating of our heart. The heartbeat is also periodic. So then the ticking of clock. The ticking of clock is periodic motion. And the bob of the pendulum. The bob of the pendulum. You can see the figure here in the slide. The bob of the pendulum, it makes oscillations in the vertical plane. So these are the periodic motion. So their motion is repeating continuously. And if you observe the vibrations of the tuning fork and a bouncing ball, next a rocking chair, you can see the rocking chair here. So the movement of the rocking chair is also periodic in nature. So let us revise the example once again. The rotation of earth around its axis, the rotation of moon around the earth, and the revolution of earth around the sun, the beating of our heart, the ticking of the clock, and the simple pendulum, then a vibrating tuning fork, a bouncing ball, and finally a rocking chair. So these are the examples for periodic motion. So these are the motions which repeating at regular intervals of time, so known as periodic motions. Then we go for simple harmonic motion here. So why we learn about the periodic motion before going to learn about the simple harmonic motion? Because the simple harmonic motion is, first of all, it is a periodic motion. The simple harmonic motion is a periodic one. So the simple harmonic motion is defined as a periodic motion of a point along a straight line. So I am mentioning that the motion of the particle must be in a straight line, such that its acceleration is always towards a fixed point in that line and proportional to distance from the point, means distance from the mean position. So this is called simple harmonic motion. First of all, what are the conditions here? First of all, it should be periodic in nature and the motion of the point should be in a straight line such that its acceleration is always towards a fixed point and it is proportional to the displacement or distance from the point. It is called simple harmonic motion. So see here. So we discussed so many examples for a periodic motion. So what is the difference between the periodic motion and the simple harmonic motion? So see here, the examples for SHM, the motion of the cradle. So if you observe the path of the cradle, what is the path? It should be in a straight line. It is in a straight line. The motion of the cradle is in a straight line. It is not in a circular path. Whereas if you observe the motion of the moon around the earth or the motion of the earth around the sun, so the motion of the earth will be in a circular path. It is not a straight line. It is periodic, but it is not in a straight line. So that is the difference between the periodic motion and the simple harmonic motion. So here it should be, the motion should be in a straight line. That is the very important condition for SHM. So the motion of the cradle, the motion of the needle in sewing machine, and the cork floating on water waves. If you can observe the crest and troughs, the water waves, the cork moving up and down. There is a up and down motion, means there is a straight line, vertical line. The motion of the cork is in a vertical line, along the vertical line. Next, the motion of the prongs of the tuning fork. So if you hit the tuning fork with a rubber hammer, what happens? The prongs of the tuning fork will be vibrates. It will be the to and fro motion. There is a to and fro motion of the prongs of the tuning fork. So to and fro motion, there is a forward backward motion. So it is also in a straight line. You can see all the motions of these examples. It is in a straight line. The motion of the pendulum clock. So it makes oscillations in the vertical plane. So what is the path of the pendulum clock? It is in a straight line. Next, the motion of the simple pendulum, same as the pendulum clock. Now the oscillations of the violin string. So if you just plug the violin string, so it vibrates, means there is a to and fro motion of the string. So it is a straight line motion. So the motion of the loaded spring, the loaded spring. So the loaded spring makes vertical oscillations in up and down motion. So this is also SHM in nature. So what are the examples? First of all, the definition of the SHM is it is defined as a periodic motion of a point along a straight line such that the acceleration is always towards a fixed point and proportional to the displacement from that point. And the examples are the motion of the cradle, the motion of this needle in sewing machine, the cork floating on the water waves, and the motion of the prongs of the tuning fork, the motion of the pendulum clock, and the motion of the simple pendulum, the oscillations of violin string, finally the motion of loaded spring. So you can see the figures in this slide, the vibrating tuning fork, a weight on the spring, so it makes vertical oscillations, a boy on the swing here, and the pendulum clock, the girl is in a cradle, next the simple pendulum. So these are the examples for simple harmonic motion. Okay, next we go for the conditions for SHM. The conditions, what are the conditions for a particle which executing SHM? So there are some conditions. Let us discuss that. The motion should be periodic. The motion should be periodic. So to explain these conditions, I just take an example here. A spring is there is a spring here, and it is loaded with a mass. So it makes oscillations. So there is a to and fro motion of the spring here. You can see the figure in the slide. So the motion should be periodic. What happens when the spring is elongated in the x direction? In x direction, there is a compression and elongation of the spring, you can see. So the motion should be periodic. So this motion will be repeats continuously. So the first condition is followed by the spring. Next, the second one, the object must move to and fro motion about the mean position. So see, in among the three figures, the center one is the mean position, and the first figure is elongation, and the third one is compression. The first one is elongation, the center diagram is the mean position, and the third one is compression. So see, the spring moves to and fro, means it is moving to and fro about the mean position. There is a compression, elongation, nothing but to and fro about the mean position, means the motion exists on the on both sides of the mean position. Means compression is on one side of the mean position, elongation is another side of the mean position. So the motion exists on both sides of the mean position. So the second condition is also followed by this loaded spring. Next, the acceleration must be directly proportional to displacement. So see here, during the elongation, what happens? The restoring force developed inside the spring. So that restoring force always acts towards mean position. So you can see the figure here. The force is acting towards the mean position during the elongation. The restoring force acts towards the mean position, whereas in the compression the restoring force is acting towards the mean position. So whereas the restoring force acting towards the mean position, the acceleration is also acting towards the mean position. So why? Because restoring force acting, then acceleration is also proportional to the force. So in both conditions, compression and elongation, we can say that acceleration is always acts towards the mean position, and it is proportional to displacement. Now the restoring force is acting towards the mean position. So this is also followed by the loaded spring. So whereas the acceleration and displacement but must be opposite to each other. See, in the first figure, the force is towards the mean position, but x is in away from the mean position. The displacement is away from the mean position. So in the third figure, so the force is in towards the mean position and x is opposite to the force. So whereas for acceleration is also, the acceleration displacement both are opposite to each other at every time. So these are the conditions. The motion should be periodic. Objects must move to and fro about the mean position. Acceleration must be directly proportional to displacement and it is towards the mean position. Restoring force acting on the body always directed towards the mean position, and acceleration and displacement always opposite to each other. These are the conditions. Now we'll discuss the projection of the uniform circular motion on a diameter is SHM. Is SHM means simple harmonic in nature. So to explain this, I just consider a particle P, uh, which is moving on the circumference of the circle of radius A. So observe the figure here. The particle is moving along the circumference of the circle. So here circle, in the circle, x dash is the horizontal diameter, y dash are the vertical diameter. X dash and y dash are the two perpendicular diameters. I just observing the two diameters. Now the particle initially at x point. The particle is initially at x point, then it moving towards y, then x dash, then y dash, and finally x. So it is moving in anti-clockwise direction, and the center of the circle is O, and the diameter and the radius of the circle is A, and it is moving with uniform speed v. Okay, then if the particle initially at x point, after t time it is moving to p point.